All right, so here's your notes. We're going to have two different types of cells, or just different arrangements of cells that we're going to look at. The one on the left is the one that has two different beakers and uses that salt bridge or that porous, or sorry, the salt bridge or the U-tube to connect the two beakers. The one on the right is called a porous cup method, and I'll show you how both work. The basic principles are exactly the same, just where things move changes slightly, but not very much. So in your notes, what we're going to focus on right now is we're going to focus on the one on the left. We're going to cover that one, and we're going to do this in this space right here down at the bottom. You're going to draw in kind of the half reaction and what's going on there. Okay, so let's hop over to this screen. I know it's not as pretty, but it gives me a little bit of room to work. So the cell that we're gonna set up here has different metals on different sides. So on this side, we're gonna label this copper solid. With the copper solid, which is our electrode, remember, we have to have an electrolyte, something that can transport the electrons, or at least the charge around. In this case, that substance, well, let me make some room here a little bit. That substance is copper 2 nitrate. So that means because that's aqueous, in the beaker itself, you're going to have copper 2 positive ions, and you're going to have nitrate or NO3 ions. Okay. On the other side, same idea. This is going to be zinc solid for our electrode, and the electrolyte is made of zinc nitrate. So we're going to have zinc 2 positive ions and some NO3 negative ions. Okay. All right. Draw this in again. Okay. We also have an external circuit that connects this side to the other side. Now, I want you to pause the video right now. Actually, no, not right now. I want you to list these out on the bottom. If we were to do like we've been doing and listed out our species, we would have copper solid. We would have copper 2 positive ions. We would have zinc solid. We would have zinc 2 positive ions. We would have nitrate ions. And then don't forget, because these are aqueous solutions, we would also have water. Okay, so once you get that copied down, pause the video. I want you to break out your data booklet, and out of these, find who would be the strongest reducing agent and who would be the strongest oxidizing agent. So pause now, figure that out. Hopefully you did it. Okay, if you did it right, you should have found that the copper 2 positive ions are my SOA, and that the zinc solid ions are my SRA. Okay, so if we were to write out our two half reactions for this, we would write the copper reaction, because it's the SOA, we would write it forwards. So if I just copy it straight out of the data booklet, copper 2 positive plus 2 electrons becomes copper solid. The zinc, same thing, but then because it's the SRA, we write its reaction backwards, right? It has to be being oxidized, losing those electrons. So in this case, I have zinc solid becoming 2 electrons plus zinc 2 positive. Okay? In this case, if we want to do our net reaction, it's fairly easy. 2 electrons gained, 2 electrons lost, they already balance. So my net reaction is that copper 2 positive ions are going to react with zinc solid to create copper solid and zinc 2 positive. So that's our overall reaction. That's what's going on here. So now let's go back up to the diagram and see if we can see what's going on. From our half reactions, we know that copper wants to get electrons. So this guy over here wants those electrons. But the only place he can get them I should have done that differently. Not the copper solid. This guy, copper 2 positive, wants those electrons, but he can only get them from zinc solid. So how do we get electrons from the zinc solid on the right to the left? And the way we do that is through that external circuit. So in this case, the electrons are going to flow from this side through the external circuit and towards the copper solid. And we know from looking at our half reactions that every time a zinc solid gives up 2 electrons to copper, it's going to send 2 electrons through the wire, and then that zinc solid is going to become zinc 2 positive. Copper, on the other hand, wants to get them, so these copper ions are going to move towards and bump into the copper solid. When they do, they're going to pick up the electrons that have been donated by zinc, and once copper gets those 2 electrons, it becomes copper solid, right, from our half reactions. So this electrode is actually going to start to grow copper solid, and this electrode will keep getting bigger and bigger and bigger the longer we let this cell run. On the opposite side, the longer we let this go, this zinc electrode is actually going to break down. It's going to get smaller and smaller and smaller because more of the zinc solid is turning into zinc 2 positive aqueous. All right, so there's kind of what's going on. I've got electrons moving from the zinc to the copper. The copper 2 positive ions are picking up those electrons at the solid. Because the electrons can't go into the aqueous solution, it has to pick them up on the surface, which means that it builds up, and my zinc solid is breaking down over time. This flow of electrons through the circuit is what we call electricity, right? You could, in the middle of that circuit, you could put an iPhone, you could put a light bulb, you could put whatever it is, and that would provide you with electricity. And we'll show you how to figure out how much here in a second. But first off, we need to go through a couple of things here. So I know that over here, that the copper 2 positive was my SOA. I know that because it's my SOA, it's gaining electrons, which means it's being reduced. So, right, we remember Leo the lion says grr. And so over here, on this side, the zinc side, the half reaction that's happening is oxidation. On the copper side, it's reduction. We're going to add a little expansion to this. Instead of just Leo the lion says Gurk, we're going to make this Leo Anderson is a Gurk. And what those stand for is that A means that this is labeled the anode, and this side is labeled the cathode. Okay, so that's the first thing you need to know. If you were to look at a battery, like a Duracell battery or any kind of normal battery, you know that they always have a positive and a negative terminal on them. The cathode is the positive terminal on that battery, and the anode is the negative terminal. So if you, for example, are looking at a battery, like let's say a car battery, you need to jumpstart your car, you should always hook up the black cable last because it's the negative terminal. That's where the electrons are coming out of, right? They're coming out of the anode or the negative terminal. They're going to flow through the jumper cables to the other battery, and so you want to make sure you hook that one up last. If you hook it up first, then that cable is essentially energized, and as soon as you connect it, then the electrons are going to start to flow. So you should hook that one up last just to make sure that everything's a little bit safer while you're doing it. Okay, so on a normal battery, you don't need to draw this, but let me just show you this really quick. Wrong pen. On a normal battery, right, let's say a AA or something like that, the positive end is up here, the negative end is down here, which means when you plug this in, electrons flow out of here through your device and then back into the positive terminal of the battery. That's how the electricity flows through there. All right, so if we go back to our objectives, let me switch back to here. You should hopefully have now these terms. So we've got anode, we've got cathode, anions and cations. Hopefully you remember from Chem 20, those just mean negatively charged ions or positively charged ions. The salt bridge or the porous cup, we'll come back to that in just a second. The electrolyte and the external circuit. Now power supply, we're not going to cover just yet. That goes with electrolytic cells, so we'll also dodge that one for now. But voltaic cell, that term is what we just drew, right? This right here is a voltaic cell. Any kind of battery that produces electricity is a voltaic cell. Now the one thing that's happening here that I didn't mention, and it's the reason for that salt bridge or that U-tube in the middle, is if you look on the left side, look at what copper's doing. Copper 2 positive is becoming copper solid, which means I'm getting less and less positive ions over here. They're dropping, their level's dropping. So that solution is becoming more negative as we remove positives out of it. If you look at the other side, the zinc reaction shows me that zinc solid is becoming zinc 2 positive. So I'm getting more and more zinc 2 positives on this side. This solution is becoming more and more and more positive. In that salt bridge, we always have positive and negative ions. Sometimes you'll know exactly what those positive and negative ions are, like there's sodium and chlorine or whatever, but sometimes we don't know. We just know that there would have to be ions there. In order to balance this charge out that's happening in the solutions, let's look, for example, at the left side first. Copper's leaving, so the solution's becoming more negative. So the positive ions in the aqueous solution in the tube would move down here to replace the copper that's being lost and to try to balance the charge in that solution. On the other side, the opposite's going to happen. Zinc solid is becoming zinc 2 positive. So it's becoming more and more positive there. These negative ions would flow down here to this side to try to balance that out. And that's the purpose. If we didn't have that connection between the two, we wouldn't be able to balance the charge there. Eventually this battery would stop working long before our electrodes ever broke down. Hopefully you can also see though why this battery may not work forever, because if I run this forever, eventually this electrode is going to be gone, right? We'll have dissolved all of the zinc and there will be nothing left to donate electrons, and then the battery dies. So, all right, that covers this first one. The second one is going to be very similar, although it's just a different setup on the top. So I'll probably leave the bottom for the next video and just change the top.